Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. And in this hour, we're going to talk about one of the most interesting topics in all of medicine, and that is the aging process. Why do we get old? Is it possible that one day we can stop the clock, reverse the aging process? Well, here's a doctor who says, well, yeah, it may be possible. He is Dr. Michael Fossel, MD, PhD from Stanford University, and author of a book, The Telomerase Revolution, the enzyme that holds the key to human aging and will lead longer, healthier lives. We should say that telomeres are, we think, the clock inside cells. After 40 to 60 reproductions, the cell goes into senescence and eventually dies. In fact, some people think that's one reason why we die. However, this enzyme may actually allow you to stop the clock. And so does that mean that this is the fountain of youth? Or should we also say that there have been hundreds of other charlatans and quacks that have claimed to have the fountain of youth? However, this one has been looked at very seriously by scientists around the world. The aging process and a biological clock governed by something called telomeres inside your cells, and is telomerase, the enzyme that can control the process of telomere reduction. Is that the fountain of youth? Well, just to be fair, we should point out that on Science Fantastic, we've had a number of other biogerontologists who claim other therapies. For example, caloric restriction. You eat 30% less, you live 30% longer. Oxidation theory, resveratrol, age genes, mitochondrial theory. There are many theories, but some people claim that one day we may have a cocktail of several of these promising scientific therapies along with telomerase, which may allow you to slow down and perhaps even stop the aging process. I mean, wouldn't that be great? However, what about society? What's going to happen to society if all of a sudden we have a bunch of old people living to be the year 200? Will society stagnate? Will Social Security become bankrupt as people live forever? Well, these are the questions that Dr. Michael Fossel is contemplating. But the difference between quackery and charlatanism and wizards making all these bizarre claims about living forever, the difference between them and the new generation of scientists is that the new generation is based on science. That is, reproducible, falsifiable, testable theories. Not just the hearsay of one person saying, I think I saw this person live forever, therefore why can't we? I mean, how do you test theories like that? How do you test them on animals? And how do you test them on humans? That's what we're going to talk about. So today, forget about all the stuff you see in the drugstore. Take 10 years off your life, be younger, be healthier. Most of that is real quackery. The Food and Drug Administration, unfortunately, does not regulate much of the junk you see in a drugstore because they don't penetrate the skin. Precisely because they don't penetrate the skin, they don't work. And so in some sense, you can only make fraudulent claims about being younger and taking 10 years off your face and whatever, only if they don't work. Well, now let's talk about therapies that might actually work in the laboratory, on animal studies, and perhaps even on human studies. Not just telomerase, but caloric restriction, mitochondrial DNA, oxidation theory, resveratrol. These are avenues of real scientific investigation. And we should also point out that at the Joint Corporation in Menlo Park, they have actually immortalized a skin cell, a human cell that lives forever in a petri dish. Okay, well, let's take a short commercial break, and after the break, we're going to talk about the aging process. Why do we have to get old? Why do we have to die? Is it possible that we can stop the clock? Is it possible that we understand it? Is it possible that we can slow it down? Is it possible that one day we might be able to reverse it? Now, let me be very clear. There's been charlatans and hoaxers and tricksters for generations talking about the promise of living forever. Kings and queens have set out expeditions hoping to find the fountain of youth, but to no avail. But what about modern science? With us today is Dr. Michael Fossel. He's a PhD and a MD from Stanford University, author of a number of books. We're going to talk about his latest book today, The Telomerase Revolution, the enzyme that holds the key to human aging and will lead to longer, healthier lives. We should also point out that he's the author of Reversing Human Aging, also Cells, Aging, and Human Disease. And he's been on Good Morning America 2020 and a number of national shows. And his website is www.michaelfossel.com. That's Fossel, one word, michaelfossel.com. So, Dr. Fossel, glad you could be on Science Fantastic.
Michio, my pleasure. Thanks for having me.
Okay, the first question that we always ask our guests is, how did you, as a youth, when you were 10 or so years old, how did you as a youth first get interested in science?
I think it's one of those things that sneaks up on you, like so many things. You know, why am I interested in gardening? Why is someone else interested in cooking? It sneaks up on you. And I discovered in high school that I was trying to take all the physics courses I could, actually set up a course on particle physics.
Is that right?
It was a delight to me.
Yeah, well, that's what I do for a living.
I know.
Go on. Okay. And then what got you interested in the question of the aging process?
What got me interested was an odd thing. It was people's responses. I was teaching courses on neurobiology and the development of the nervous system, but whenever I talk about the other end of life, how does the nervous system fall apart, for example, of Alzheimer's, people tended to shrug and say, well, it just happens. And any time people say things just happen, it gets my goat. I begin to wonder what we're missing. I suspected there was a lot more to it than that, so off I went.
Okay, now here's a big question. What actually is aging anyway? Because, of course, kings and queens, they have spent entire fortunes looking for the fountain of youth, as if youth could be encapsulated in a liquid or an elixir. What do you think is aging, therefore?
Well, so many people think of it as just entropy. That is, as it were, things just fall apart, they just rust, things come apart over time. What do you expect? But as a biologist, you have to recognize that all living things are sort of a balance between entropy and maintenance. That is, aging is not simply entropy. It's a failure of maintenance. That's why, you know, we look at dogs and they age faster than we do. Progeric children do. Bacteria age quickly, or at least yeast organisms do. Other things live longer than we do. It clearly isn't a matter of just entropy. There's more to it than that. And again, anytime people say it's, quote, just entropy, it gets me curious about what we're missing. I've long suspected that aging was a much more complex phenomenon than it just happens, or it's just entropy. Again, biologically, it's a failure of maintenance in the face of entropy. And it doesn't always happen. You know, there are cases of cellular lines that don't age. Example. You right now are presumably several decades old, and you got the bulk of yourself from your mother. She got it from her mother. And when you inherited it, that cellular line hadn't aged and had been in existence for probably about 3.5 billion years, looking backwards. Well, how come that cell line didn't age, and yet you and I age in a matter of decades? There's clearly something going on more than it just happens.
Okay, now there are many approaches to the question of aging. Some people say, as you correctly pointed out, entropy. Things break down, DNA begins to wear out and not perform as good as it used to. However, we also had Dr. Leonard Hayflick on the airwaves, and he claims there's something called a biological clock, that maybe the clock is ticking away and it was reset when we were born. But what are your thoughts about whether there's a biological clock in our bodies?
Well, I think that's exactly it. I have to say, Len is my favorite curmudgeon in the world. He's a hero of mine because he's one of those people, as you look back historically, who had the guts to stand up and say, you know, here's what everyone believes, and they're wrong. And that's happened repeatedly, whether it was, the idea that the Earth was the center of the solar system, or that physics was no more than classical physics back 100 years ago, or that aging just happened. Now, what had happened was everyone was saying that cells don't age. They only age when you're in an organism. And Len stood up back more than 50 years ago and said, that's just not right. Cells do age. And it wasn't clear when Len said this what was the biological clock. But since that time, it's become a lot more clear what's going on. And it's also become clear that aging is not simply a matter of DNA failure or hormonal changes. No, it's something far more basic than that. It has to do with the pattern of gene expression. something that Len couldn't put his finger on when he first published. And yet, since that time, the evidence has accrued and gotten more and more substantial.
Now, my understanding is that Dr. Hayflick showed that cells, like skin cells, divide roughly 50 to 60 times, and then they begin to go into senescence. They begin to wear out. And so in some sense, all our cells have a clock in them, and when time is up, cells begin to age and die. But could you elaborate on that theory?
Well, that's interesting, because it clearly is true of certain cells, but not others. Example, we sort of wish cancer cells would age, and many cancer cells don't. They continue to avoid senescence. They don't sort of degrade in that way. They divide when we wish they would die. But the same is true of germ cells, that is, ova and sperm cells, and as they say, you follow the cellular line of humanity back as far as you want, and that cell line didn't age. We also know this is true of certain stem cells. They either don't age, or in certain cases, they age much more slowly than other cells. So when Len talked about the Hayflick limit of, say, it was 40 to 60 divisions, it depends on which cells you're looking at. It also depends on which species you're looking at. So again, just to say that all cells senesce or that all organisms age, both are wrong statements. It's more complex than that. Some cells don't age or don't age as quickly. Some organisms age more quickly or less quickly.
Okay, well, according to the theory, and you can elaborate, our cells, of course, have chromosomes inside of them, and at the ends of the chromosome, there's something called the telomeres, and they get shorter after every reproduction. And after 40, 60 reproductions, the telomeres get so short, they wear out. Could you elaborate on that, the fact that at the ends of our chromosome, there could, in some sense, be a clock that gets shorter and shorter with every reproduction?
Yeah, we first discovered that now, well more than 20 years ago. It was the early 90s. Around 1990 was the first study out that suggested there was a good correlation between telomere length and cell aging. Now, since that time, we've discovered a lot of interesting things. One is, it's not the length of the telomere that matters. It's the change in length. Secondly, it doesn't matter what the telomeres are doing. The key feature is the change in gene expression. You can have long telomeres or short telomeres. In fact, there are mice with telomeres much longer than ours, but they have shorter lifespans. It's the change in length, not the absolute length. But a much more important finding is what happens when you reset that length. That is, if I take old cells with relatively short telomeres and reset them, do you improve cell function? The answer is yes. First discovered that in 1999. If somebody ever said to me, when did we first show that we could reverse aging? Well, in the cellular sense, the answer was 18 years ago. In the tissue sense, it was 17 years ago when we first showed we could take old cell tissues, for example, human skin or human cells from coronary arteries, reset the telomeres and show you could grow young tissues from them. The more important question is, can we do that not only in animals, but more importantly to you and I? That is, put it bluntly, can we cure age-related diseases? That's about where we are now. The animal studies are very interesting, but the human studies have yet to be undertaken yet.
Okay, well, some people say, and you can elaborate again, that an enzyme called telomerase, which is the subject of your book, in fact, can stop the clock. That is, if there's a clock ticking away inside our cells, and the obvious question is, can you stop the clock, reset the clock, slow it down, or even make it go backwards? So tell us a little bit about what is telomerase.
Well, telomerase is an enzyme, and an enzyme is just a protein that does something. It's sort of the verb form. It is active. It does something to you. So, for example, you can get enzymes that break down sugar or break enzymes that help you burn calories, all sorts of enzymes. And telomerase is just an enzyme. But what it does is something that no other enzyme does. It resets the aging clock in cells. And you asked the right question. Can we stop aging? Can we reverse aging? In cells, there's no doubt we can. John Cook at the Houston Methodist Hospital just published an article a week or so ago showing he could reverse that in progeric cells, that is, children who have early aging syndrome that can be reversed. Well, we actually knew we could do that in human cells, as I say, 20 years ago. I first put out the articles in JAMA 20 years ago this year, suggesting this was a good thing to do. We should try that for progeric children, for example. But it's only more recently that we've gone beyond that and shown that not only can you reset the aging process in cells and tissues, but we can apparently reset them in animals. For example, there was an article that came out now about 4 years ago Well, actually, there was one 5 years ago out of Harvard showing we could do this with a technique I couldn't apply to patients. But about 4 years ago, a colleague of mine in Madrid showed that she could reset aging in animals themselves, not just tissues or cells, and reverse many of the changes that we see with age-related diseases. So things have gone a lot further than people realize, and yet there's a lot we don't know, and there's a lot we haven't done to human testing yet. So it's still an open area.
Okay, well, I heard a story that at the Geron Corporation, they've taken ordinary human skin cells, put them in a petri dish, hit it with the enzyme telomerase, which stops the clock, and these cells, instead of dividing 40, 60 times, they divided hundreds, maybe even thousands of times, and they have been immortalized. In fact, there's a new word in the English language, to immortalize a cell. What are your thoughts about this?
Well, I think that's entirely possible. It depends what you do with telomerase. If you just put it in once, you can reset the telomere length, reset aging in cells, and then you just, instead of having a few more divisions left, you can go right back to having, say, 40 or 50 divisions. But if you put in the gene and allow it to continue to express itself, then yes, you may have immortalized the cell in the sense that it doesn't have 50 or 60 divisions left. It has an indefinite number. We just don't know. So it depends exactly what you do. The key from my perspective, and I think for a lot of us, is not a philosophical question. I often used to say when I was executive director of American Aging Association, I used to say that most of the theories of aging aren't theories because you can't actually test them. They're philosophy. And that's interesting, but that's not science. But what we're interested in is not only testing these things, but taking them to a practical human outcome. From my perspective, and again, I think many people share this, the question isn't so much what is aging or what is Alzheimer's, for example, but what's the most effective clinical way of reversing it? That is, can we cure these things? Not just talk about them, but do something about them.
Okay, well, some people say that, telomerase may allow you to, quote, stop the clock. However, cancer cells are also immortal, and apparently they just live forever, keep on dividing. In fact, that's why they kill you. That's why cancer cell is so dangerous, precisely because they are immortal and divide forever, creating a tumor. That cancer cells also use telomerase as a trick to immortalize themselves, to become lethal. So what are your thoughts about that?
Well, that's partly true. And anybody who ignored that concern, I think, would be naive. But what you have to remember is a few things. One is that telomerase doesn't actually cause cancer. What it does is it permits cancer. There are at least two stages before that have to sort of go awry before you can end up with cancer, one of which involves gene damage itself, that is mutation, and the other of which involves sort of bypassing what's called a cell cycle breaking system. And only after that does telomerase become the final hurdle in a sense. So telomerase doesn't cause cancer. Telomerase is a ways down the road, but still, for a cancer cell to continue to divide, it needs something like telomerase to
Okay, Dr. Fussell, we're going to have to take a short commercial break, but after the break, we're going to continue a discussion of your book, The Telomerase Revolution, the enzyme that holds the key to human aging and will lead to longer, healthier lives. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to talk about the human aging process. Well, on Science Fantastic, we've had a number of the world's leading experts talking about their research in the area of human aging. And some people think that we are close. We don't quite have it yet, but we're close, tantalizingly close to something resembling the fountain of youth. With us today is Dr. Michael Fussell, MD, PhD from Stanford University. He's written several books, including Reversing Human Aging. His latest book is called The Telomerase Revolution, the enzyme that holds the key to human aging and will lead to longer, healthier lives. Well, Dr. Fussell, in the previous segment, we mentioned the fact that every cell, or most cells of the body, have this biological clock. The telomeres at the ends of the chromosome get shorter after every reproduction of the cell. After 40 to 60 reproductions, the cell pretty much uses up its allotted time. But there is an enzyme called telomerase that allows you to stop this process. But hey, cancer cells also immortalize themselves, because what is cancer? Cancer in some sense is a cell that becomes immortal and it simply divides in perpetuity, creating a tumor which eventually kills you. So the question is, what are the side effects? What are the implications if we were to use this as in the future as a form of therapy?
Well, you're right to raise that cancer issue. Now, I have to say that was a concern we had 20 years ago, and it still sort of has hung around as a sort of a boogeyman. But theoretical considerations, which I'll mention in a minute, make that less likely that it's a problem. And the data shows it is less of a problem than we thought too. What we've realized is that telomerase, when you re-extend telomeres, you actually improve the ability of cells to repair DNA. So they act like young cells. That is, they repair DNA much faster, much more efficiently. So what we've discovered is that telomerase is actually protective of the genome. It sort of stabilizes the genes in the face of mutation. So while we've been talking, probably every cell in your body has had a genetic mutation, but you've repaired them. But that rate of repair goes down with age, which is why we get more cancers as we get older. But we can reset that. So the question is, what happens when we do reset it? And again, in both cellular studies and in animal studies, we find that there's no actual increase of cancer risk, although it's, again, as you might expect, not quite that simple. It depends on the exact length of the telomere. If it's very short and you extend it a little bit, you don't improve things. You may actually increase the risk. But if you fully extend it, you end up decreasing the risk. Most cancer cells actually have fairly short telomeres, but just enough to divide, not enough to undergo full DNA repair. So we suspect that we'll have a lot less risk of cancer, as we see in animal studies, when we take this to human studies. But that's one of the reasons that our primary target is going to be fatal diseases like Alzheimer's rather than cosmetic problems like wrinkles. We intend to find out just what the risk is, but we suspect it's a lot lower than we used to think it was 20 years ago.
Okay, well, somebody listening to the show may say to themselves, wow, I mean, you're talking about a therapy that may allow you, at least at the cellular level, to slow down, maybe even reverse the aging process. But then the next question is, what about human studies, not animal studies? Humans are more complex in our biology. So what has been done in terms of human studies?
Well, there have been some informal, I guess I could call them human studies. And what they've looked at is some telomerase activators, in this case, the astragaloside. And I know of 3 peer-reviewed papers that have come out on this, and all of the results are interesting. I'd have to say they're very intriguing. And they show some significant changes, but nothing overwhelming. You certainly don't see that somebody who's 70 years old now becomes 30 years old. But what you do find is that their immune systems act a little better, their ability to handle glucose and insulin work a little better. A lot of tantalizing results. What we have known, though, for a while is that these telomerase activators are not all that effective. Perhaps they're 5% as effective as we'd like to be. And that's in line with the data. So there's intriguing data out there, but nothing that is overwhelming, just intriguing.
Okay, Dr. Fussell, on this radio show, we've had a number of biogerontologists talking about things like caloric restriction. And they claim that if you take an animal, no matter what the animal is, starfish, spiders, worms, all the way up to primates, and you feed them 30% less calories, they live 30% longer. And they claim that this is the only proven method that works across the genome that allows you to increase the lifespan of animals, except humans, of course, because we bellyache too much. We don't want to live on a diet of 30% less calories. But what are your thoughts?
Well, we have known for a long time being multiple decades, that there are 3 things that can alter a lifespan of an animal. One is caloric restriction. You're quite right. The data is substantive. It hasn't really been proven with human beings, but that's because we have such long lifetimes. It's hard to do the experiment very well. The second is you can selective breeding. That is, you can take any animal we've ever known about and breed them for a longer or shorter lifespan. That doesn't help you and I clinically. The third is genetic intervention. Most of the genetic interventions have been negative. That is, you can certainly make animals have a shorter lifespan. But we found cases where you can actually improve the lifespan of an animal with genetic alteration. And that's really what we're talking about today. We're talking about not really genetic intervention in the sense of changing the gene, but we're talking about what you might call epigenetic intervention, that is changing the pattern of gene expression. And again, that's been shown to work very well. So when people talk about caloric restriction, they're right. In some sense, we should all eat less. The problem is we're really living in the experimental group where we're all eating too much, and we know that that's not healthy at all.
Okay, well, some people go one step further and say that there's a gene called the sirtuin gene that helps to regulate this process, and the protein or the enzyme created by the sirtuin gene is called resveratrol, and quite frankly, it's created some kind of a blip on conspiracy theorist websites who claim that perhaps that's the secret fountain of youth. I tend to disagree, but what are your thoughts about those people who swear by enzymes like resveratrol, which may slow down the oxidation process? What are your thoughts?
Well, I find myself agreeing with you, which doesn't surprise me one bit. I think it's like the blind men and the elephant. They're looking at a small piece of the elephant rather than the whole elephant. And they are right in a sense, in that any time you find an abnormal process, for example, the processes we're dealing with caloric restriction or DNA repair enzymes, if you just sort of fiddle with that one system, you can find improvements or you can find ways to ruin the system. And that doesn't surprise me. But what we're talking about when we're talking about aging generally, or in this case, telomerase and gene expression, we're talking about all of those processes together, not just one, but everything. Think of it as dealing with one person in a country versus dealing with the entire population of the country. So if you have thousands and thousands of genes and you're affecting just one gene, that may have a good effect or a bad effect. But what we're talking about is affecting the expression of all of those genes. So it's a different order of magnitude.
Okay. Now, there's yet another theory. There are several theories. This theory says that just like a car engine ages because of oxidation in the engine, because of carbon buildups and wear and tear, the engine of a cell is the mitochondria. Therefore, damage to the genes of mitochondria, just like the damage to the genes of an engine in a car, is responsible for it wearing down. So what are your thoughts about looking at the genes that are damaged in the mitochondria, which some people suspect is similar to damage in the engine of a car?
Well, let me say this. Right in front of me, I have a slide that shows a 1930 Duesenberg car, and it is absolutely gorgeous. And I think about the car I'm driving, which is probably about 5 years old and has some rust spots and some dents and is not in as good shape as that 1930 Duesenberg. Well, the reason is not because the Duesenberg was better built. It may be, for all I know, than my Ford. But the difference is maintenance. That Duesenberg was taken care of over 5 or 6 generations.
Okay, unfortunately, we have to take yet another short commercial break. Stay tuned now for the next segment. Welcome back to Science Fantastic with Professor Michio Kaku. The book is called The Telomerase Revolution. That's Telomerase. With us today is Dr. Michael Fossel of Stanford University, where he got his MD and PhD degrees. And we're talking about, well, is it possible to slow down the aging process? Before the break, we talked about the mitochondrial theory. That is, just like the engine of a car is where aging takes place because of the wear and tear, moving parts, combustion, and so on and so forth. The engine of a cell is called mitochondria, and therefore by looking at the breakdown of the genes in the mitochondria, we can isolate where most of the wear and tear of the aging process takes place. So, Dr. Fossel, what are your thoughts?
Well, it turns out that every mitochondria you have in your body, you got from your mother, she from her mother. Now, that cell line is called eukaryotic cell line, and the mitochondria have been in that cell line for about 1.5 billion years. They didn't age, and yet they age in a matter of decades in you and I. It turns out that the key has to do with telomere again. It turns out that most of the aerobic enzymes, the enzymes that are responsible for mitochondrial function, come from the nucleus, and those all have a lower rate of expression as a result of telomere shortening. So while mitochondrial changes are critical, it turns out they're secondary. And again, secondary to gene expression, changes that occur because of mitochondrial changes. So again, the theory holds together pretty well, and we can reset it.
Okay, now let me talk about the societal implications. Some people say that, well, we were not meant to live forever. What happens if we have a society of old people in nursing homes? Won't society stagnate? Won't our Social Security system go bust? What are your thoughts about what happens if we do live forever?
Well, first of all, let me say we will never live forever. If nothing else, you'll slip in the bathtub and that'll be the end of you. But more realistically, remember that the average age of people in any culture has increased enormously over the past several centuries. You know, it used to be, if I went back about 200 years ago in the United States, it was about 25, and 100 years ago it was about 50, and now it's about 75. So it's certainly true that people are living longer on the average. And I'm not sure what social changes that's created in our culture or in any other part of the culture, in any other culture in this world. But this is not a new phenomenon. And what we're not going to see is people living for thousands and thousands of years. But what you will see is people living and being healthy for a good deal longer than we are now. It wouldn't surprise me to have a mean healthy lifespan of 150 or 200. Again, healthy lifespan. We'll just have to see how far this goes. It should have enormous societal effects. What those are unfortunately difficult to predict. I sometimes say that the personal outcome of doing this is all to the good. The idea of not having a heart attack, not getting Alzheimer's, not getting osteoarthritis are enormously beneficial to you personally. The societal benefits are hard to estimate.
Okay, well, some people point to Japan, which has the longest-lived ethnic group for 20 years running on the earth, that is Japanese women. And the Japanese population, instead of exploding, is contracting. Japan will eventually lose about 1 million people per year by mid-century, because as you live longer, you have fewer children. You space them out more, have fewer of them. And so some people think that as people live longer, we're going to have the opposite effect. We're going to have an implosion, just like what's happening in Japan and will eventually happen in Europe. What are your thoughts?
Well, that's been true, actually, in a lot of European countries and in the U.S. now. If what you're looking at is not immigrants, but what you're looking at is population that started there, that is, the birth rate has been falling in most developed nations. And so the estimates are that the world population, instead of just increasing exponentially, may in fact go into a decline fairly soon in the next century or so. And estimates vary all over. But what we're talking about is a little different. For one thing, people live longer, so the population stays around. You may have fewer children, and yet you have a longer lifespan. The other complete unknown is, what does telomerase do to human fertility? And there's no way really to tell. There are lots of arguments I can make on both sides, but it could be that we're extending the fertile years of women, for example, men certainly, and it's just hard to predict that. What outcome that has for a world population is, again, an unknown. Let me put it this way. The simple answer is this. I sometimes call it Fossil's rule of thumb, because there are about a dozen big variables and dozens of little variables. But the quick answer is simple. If you double the mean human lifespan, you double the population. That's sort of the quick rule of thumb. So if we increase the healthy human lifespan, we can expect to have more people. That's independent of birth rate, though.
Okay, let me ask you a key question. Do you think that in the future we'll have a fountain of youth? It could be a cocktail of different kinds of different therapies, but do you think we'll have it perhaps in 10, 20, perhaps in 50 years? If you had a crystal ball, do you think we'll have a fountain of youth of some sort, and roughly by when?
Well, let me again say what I said before, which is if somebody went to the future and said, when did we first reverse human aging? The technical answer is 18 years ago, when we did it in human cells. But the practical question is, when will we do it to you and I? And if what we're talking about is not a fountain of youth in the sense of living forever and being 20, but at least demonstrating that we can reverse much of the aging process, I think we'll be able to demonstrate that within the next 24 months, frankly.
The next 24 months?
I think so, but let me put it differently. If I go to the FDA and said I had an anti-aging therapy, their policy, I think it's appropriate, for the last 20 years has been not to be willing to look at any FDA trials that involve reversing aging. What they're asking us to do, all of us, is to come to them with a trial that looks at an age-related disease, for example, Alzheimer's disease. So I think that we'll be able to focus on specific age-related diseases and demonstrate we can reverse some of these age-related diseases, and that the first demonstration will occur within the next 2 years. Yes.
So you think that the fountain of youth is not out of the question? Is that what you're saying?
Well, I wouldn't want to call it the fountain of youth, but at least the fountain of not having so many age-related diseases. I guess I take a more practical bent.
Okay, good. Well, unfortunately, our time is up. Once again, thank you so much for being on Science Fantastic. Our special guest has been Dr. Michael Fossel. The book is called The Telomerase Revolution, the enzyme that holds the key to human aging and will lead to longer, healthier lives. His website is www.michaelfossel.com, one word, Fossel.com.
Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing developments in science and technology that affect our lives. And in this hour, we're going to throw the lines open because this hour is your hour. Okay, well, let's move right on now to the first listener phone call.
My name is Richard. I listen to the podcast off of Stitcher Radio. My question is regarding the discussion on the center of the universe, and I know people have asked over and over again about, the no center of the universe. My question is aren't the galaxies moving away from each other? Isn't that like proof that there is a center of the universe? Thank you.
Well, you ask a very interesting question because back in the 1920s, there was a huge debate among astronomers as to how big the universe was. The standard position of astronomers back in the 1920s was that the universe was the Milky Way galaxy. Period. End of story. The Milky Way galaxy that you see coming out every night, that was the universe. And how big was the universe? Well, the Milky Way galaxy was estimated at roughly 100,000 light years across, and that was it. That was the end of the story. However, there was a renegade point of view proposed by other people that perhaps the universe was much bigger than the Milky Way galaxy because there were clouds out there, clouds that were called spiral nebula, clouds that did not fit the usual pattern of ordinary stars. Then comes Edwin Hubble, the greatest astronomer of the 20th century, who then calculates the distance to these wisps of smoke out there in outer space, these clouds, and much to his shock, he found that they were literally millions of light years away, and then he calculated the redshift. The redshift caused by the fact that objects move away from you. If they're yellowish, then if an object moves away from you, light is stretched and becomes reddish as a consequence. And he found that the farther a galaxy was, the faster it was moving away from you. Immediately, this sent shock waves because it meant that A, the universe was much bigger than we previously thought. Millions, maybe billions of light years across, not just 100,000. And second of all, the universe was expanding. And then people asked the very same question that you just asked. If the galaxies move away from us, then are we the center of the universe? Well, astronomers, of course, had this bruising debate during the time of Copernicus hundreds of years ago, when Copernicus said that perhaps the sun was the center of the universe and not the earth. And over the centuries, people got used to the idea that, well, maybe the universe had no center at all. And now we have the fact that it was expanding. So if the universe is a balloon of some sort, this is the analogy that every astronomer uses in astronomy class, and you paint dots on this balloon and you inflate the balloon, then at any point on the balloon, you think that all the other points on the balloon are moving away from you. In fact, the farther it is away from you, the faster it moves away from you. So once again, if I have a balloon with spots on it, you're sitting on one spot called the Milky Way galaxy. All the spots are moving away from you, but the balloon has no center. In fact, at any point on the balloon, every point thinks that they are the center of the universe because all the galaxies are moving away from it. So then you see that the universe has no center. It's uniformly blowing up from any point of view. Then the next question is, well, what is the universe expanding into? This, of course, has caused tremendous debate among astronomers. The leading theory, which is not yet proven, is coming from string theory, and that is the universe is residing in a much bigger space called hyperspace, 11-dimensional hyperspace, and our balloon is an ordinary 3-dimensional balloon expanding in a higher dimension. So what is the universe expanding into? The 11th dimension. And if you want to read more about this hyperspace theory, get a copy of my book, Hyperspace, and also Parallel Worlds, books that high school kids have written to me about, and books which hopefully answer the question, if the universe is expanding, what is it expanding into? And by the way, if you're a bug on a balloon, and the balloon is expanding, from where did the balloon expand from? There's no point on the balloon from which it expanded, because of course the balloon expanded in the third dimension. So from a bug's point of view, the third dimension is hyperspace. Okay, well, let's move right along now to the next listener phone call.
This is Hunter calling from Cape Girardeau, Missouri. I was wondering if you could explain exactly what dark matter is. Thanks.
Well, it turns out that we're going to have an eclipse pretty soon. I'll be speaking in Missouri at Southeast Missouri State University, not far from where you are. Anyway, dark matter is a new form of matter. Every high school textbook on the planet Earth says that the universe is mainly made out of atoms. That's it. From hydrogen to uranium and a few elements beyond that, that's what the world is made of. Wrong. We now realize that we jumped the gun, that most of the universe is actually not made out of atoms at all. And we first discovered that by looking at galaxies. Galaxies rotate, but they rotate 10 times too fast. By using Isaac Newton's laws of motion, we can show that the spinning of galaxies spin 10 times too fast, and by rights they should fly apart. We should be flying apart. The Earth is a byproduct of the fact that the Milky Way galaxy is stable, but it shouldn't be. By rights, the universe, the galaxy should fly apart. So, astronomers had to invent something called dark matter, which is invisible, which surrounds the galaxy, keeping it intact. Now, that was just a theory. Now we have maps of dark matter, because when light goes through dark matter, it bends. Even though dark matter is invisible, light will bend as it goes through dark matter. And using computers, that gives us beautiful maps of dark matter throughout the universe. And sure enough, it turns out that every galaxy has a halo surrounding it, a halo that keeps it together. What is dark matter? We don't know. We think it's a new subatomic particle. The leading theory is coming from string theory, which says that the next octave, the next vibrations of the string, beyond the proton and the neutron, is dark matter. And dark matter is made out of something called sparticles. Sparticles are superparticles predicted by superstring theory. The theory has not yet been verified, but dark matter has definitely been seen, quote-unquote, using telescopes that allow you to calculate the bending of starlight. What is it? We're not sure. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Let's take the next listener phone call.
My name is Jason. I'm calling from Coalinga, California. I'm driving along the freeway. I don't know what radio station. Would it be possible to build a super highway, continental highway across the Bering Straits, and then a super highway from the tip of South America down to Antarctica, and then tunnel through the Antarctic continent, and have another land bridge or another superhighway cross over to Africa to eliminate the pollution of the oceans with all the ships? Thanks. Well,
you ask a pretty tall order. Let me say that the short answer to your question is yes. There's no law of physics that prevents us from building these gigantic land bridges, especially given the fact that the North Pole is beginning to thaw out, meaning that the fabled Northwest Passage may actually be possible. And nations like Russia are looking very seriously at new trade routes precisely because of the fact that the North Polar region seem to be thawing out. So yes, land bridges are possible, but the bottom line is cost. It's very expensive to build these things, especially when you have to go between tundra, ice, land. And not only are they expensive, but you have to justify the cost. It has to be self-sustaining, not just building it, but you have to have revenue, tax revenue or levies, some way by which you can pay for the maintenance of such a gigantic object. And realize that the history of maintenance is not very good. For example, in New York City, where I live, we have bridges that almost fell apart because they're not maintained properly. Every mayor of New York says that they're not going to fall. These bridges will not fall while I'm mayor. Let the next sucker worry about it. And so mayors chronically do not maintain these bridges because the next mayor will have to suffer the consequences if they fall. And that almost happened once several years ago when a subway, I think it was a D train, was traveling along one of the bridges and almost fell over as a consequence. And so as a consequence, what I'm saying is, yes, it is possible to build these superhighways, but the more practical consideration is cost and maintenance. Sorry about that. Okay, let's move on to the next listener phone call.
Hi, this is Mark calling from Florida, and I'm just wondering if the planet was hit by an asteroid as big as the one that took out the dinosaurs, could it affect the rotation of the Earth, like maybe slow it down or speed it up? And could it actually move it a little closer or a little further away from the sun? Thank you.
Well, the short answer to all your questions is yes. Believe it or not, asteroids can actually be used to move the Earth and make it rotate at a different rate. In fact, some astronomers have pointed out that one day the sun will expand to eat up the Earth, and at that point we may have to move the Earth. Now, how can you do that? How can you move a planet? One suggestion that has seriously been proposed by astronomers is to have the orbits of asteroids modified so they whip around. They whip around the Earth, giving a slingshot effect. They won't touch the Earth, they simply whip around the Earth, and as a consequence, the gravitational attraction nudges the Earth slightly out of orbit, and in this way you can actually move the orbit of the planet Earth with a succession of asteroids that whip around the planet Earth. This, of course, is for a very advanced civilization. It's not for us. Also, giant earthquakes. If you have for example, a Category 9 earthquake on the planet Earth, you can actually calculate the fact that it will change the rotation of the planet Earth and the orbit of the planet Earth. Now, how do you do this? Because you take an estimate of how much dirt was rearranged by a gigantic earthquake. If I have a tsunami, the original subduction zone could be several hundred miles long. Therefore, you can get a rough estimate of the total volume of dirt that was moved, and then you calculate what is called the moment of inertia. The moment of inertia is what we physicists calculate when we calculate how bodies rotate. And yes, it turns out that the moment of inertia is dependent upon the distribution of matter inside the planet Earth. And in that way, you can actually show that Category 9 on the Richter scale earthquake can change the rotation of the Earth by about a millionth of a second. Not by much. But yes, it turns out that gigantic earthquakes will affect the rotation of the planet Earth, and meteorite collisions can also do the same. 65 million years ago, we think that an object about 6 miles across slammed into the Yucatan of Mexico. Not only did it slightly modify the orbit of the Earth, it actually sent a shock wave all the way through the Earth to India. Some people claim that it was volcanic activity near India that caused the disruption of the atmosphere that killed the dinosaurs, not the asteroid. But maybe it was a 1-2 punch. Some physicists estimate that the shock wave created by the asteroid that hit the Yucatan of Mexico was so severe that it sent a pulse right through the planet Earth all the way to India, breaking the crust of the Earth near India, and perhaps that caused the volcanic activity in India. So perhaps the dinosaurs were wiped out by a 1-2 punch. So in other words, to answer your question, yes, indeed, asteroids can modify, though not by much, modify the rotational rate of the Earth and even the orbit of the planet Earth. And some people have actually proposed that as one way far in the future to move the Earth if we're faced with a astronomical catastrophe if the sun begins to increase in size. Okay, well, let's move right along to the next listener phone call.
This is Mike. My question is, why is it that when you have giant stars which are capable of collapsing and creating black holes, why is it that before they collapse, their gravity is not great enough to stop the light from escaping them, but after they collapse and create a black hole, that gravity is too great to allow light to escape, when before and after the mass is the same or even less because some mass escapes during supernova? So I guess my question is, why is the gravity greater afterwards when there is no increase in mass?
Well, you ask a very interesting question. It turns out that the mass before and after the collapse is the same. So if you're a very far distance from a star that's dying and the star is collapsing into a black hole, the gravity that you feel from a large distance is the same. It doesn't change at all. However, as you get closer to the black hole, then of course you can start to see distortions. First of all, even far from the black hole, light will bend. Light will bend as it goes around a massive star as it collapses. But then, after the collapse, it turns out that light inside the black hole cannot escape. But light from the outside can very easily whip around the black hole and meet your eyes a good distance away. So there is a sphere surrounding the black hole called the Schwarzschild sphere, or the point of no return. Light inside the Schwarzschild sphere cannot escape, as you pointed out. But light outside the sphere can wrap around the sphere just as if the sphere wasn't there at all. It was just an ordinary piece of matter that didn't collapse. So to summarize, from a far distance, whether or not the black hole has collapsed, the gravity is the same. I repeat, the same far away from a black hole, whether or not it has collapsed. The only difference is the collapse itself. The difference takes place in this invisible sphere called the Schwarzschild sphere, with a radius called the Schwarzschild radius. Inside that sphere, light cannot escape. But light outside the sphere can certainly whip around the black hole. So there's no contradiction between the before and the after picture. Okay, well, let's move right along now to the next listener phone call.
My name's Steve. I'm calling from New Mexico. My comment is the whole hydrogen thing and wind. And I'm thinking that, okay, if you have a vehicle, okay, and the vehicle is moving, it's creating wind power. So why can't you use that wind power to then convert the hydrogen into energy?
Okay, well, you're asking a question. That is, if I have hydrogen or whatever that propels a car, it creates wind, and why can't you use the wind to generate energy? Well, you can. However, you lose energy in the process. And this is the first law of thermodynamics. So when you convert energy from one form to another, the total amount of energy conversion is the same. You don't lose energy, but you lose energy in the form of waste heat and vibrations and sound and stuff like that. So if you take energy from a car and convert it to convert it to electrical energy, you lose some energy in the process. Now, for example, think of your own car. Your own car has downtime, and so the wheels of the car will actually generate electricity, which is then used to recharge your car batteries. And so when you are low on your car battery, what do? You drive your car. The excess energy created by your car is used to recharge your batteries. So in that sense, we do use this principle. We use the principle that, yes, you can take the excess energy and use it to recharge your battery. And you can also do that with wind power, but like I said before, you lose energy in the process. That's also the second law of thermodynamics now. And so it's not practical. And so, in other words, it is possible that some of the wind power could be used to, for example, recharge your batteries, which we already use when your tires start to move. However, it's not that practical because you're not going to get that much energy because you get energy loss. So the answer to your question is yes, it's possible, but some inventor has to make it economically practical as well. Okay, let's move right along to the next listener phone call.
This is Bill from Portland, Oregon. And the question I have, the prediction that Professor Hawkins has made that we need to depart from the Earth and go to another planet because eventually the sun will destroy the Earth. And I'm just wondering if that is true, what are the physics behind that type of happening? Thank you.
Okay, well, the physics behind that statement is rather solid, and that is in about 5 more billion years, the sun will exhaust most of its hydrogen fuel and then turn into a helium-burning star. At that point, it'll begin to expand very rapidly, expand so much that the orbit of the Earth will be inside the atmosphere of the sun. In other words, we will have one last nice day 5 billion years from now. The sky will be on fire. The sun will expand from horizon to horizon, and the sky will be on fire, meaning that the mountains will melt, the oceans will boil away, and the earth will go back into the sun. So the Bible says, from dust to dust, ashes to ashes. Physicists say that from stardust we came, and stardust we will return. Now, how do we know this? First of all, in the 1930s, it was first worked out how stars shine. And from that, we can determine all these parameters. But let's take a short commercial break. And after the break, I'll say a few words about how eventually the Earth must return back into the sun. Okay, well, let's move right along to the next listener phone call.
Dr. Kaku, my name is Dieppe. I call from Arizona. I listen to on 104.1 every Saturday night. I want to ask why we're not able to launch a missile into orbit carrying large tether, large cables and then lower those cables from space onto the Earth and tether them to the Earth to make it easier to get stuff in and out of space, and maybe even tether the space station to the Earth and use the centripetal force to hold it into place and to provide gravity. Thank you very much. Love, Mr. Kaku.
Well, very interesting. You propose what is called a space elevator. Now, back in the 1800s, when they were building the Eiffel Tower, a physicist in Russia was fascinated by that. It was in all the newspapers. They're building the Eiffel Tower. And he asked himself a simple question. What happens instead of stopping, you just kept on going? You just kept on going to create a tether into outer space. And he realized, my God, you can create a space elevator. So you hit the up button and go into outer space. So let's take a short commercial break. And after the break, we're going to talk about the space elevator. Will that revolutionize space travel? Welcome back to Science Fantastic with Professor Michio Kaku. It's your hour in this hour. This is when you can give us a call and get on Science Fantastic. Give us a call by calling the magic number. Well, before the break, we had a question. What happens if you could create a tether from outer space to the planet Earth so you could ride this conveyor belt into heavens? That's called a space elevator. When Tsiolkovsky first proposed this in the 1800s, people scoffed at the idea and said, well, what keeps the elevator afloat? Why doesn't it fall down? And he said, centrifugal force. Think of a ball on a string. When you spin a ball on a string, why doesn't the ball fall? Because of a balancing of centripetal and centrifugal force. That's why the ball doesn't fall. So think of a tether going into outer space with a ball at the end of the tether. The Earth spins. At the surface of the Earth on the equator, you're moving at 1,000 miles per hour. 1,000 miles per hour on the circumference of the Earth. That's because the Earth is about 24,000 miles in circumference. and there are 24 hours in a day, so you divide, bingo, you get 1,000 miles per hour. That's how fast you are traveling just by doing nothing on the equator. Now launch a ball from the equator into space connected with a tether. The ball is a ball on a string. It goes around the Earth, and it never falls. It never falls because it's centrifugal force. So this was a great idea. But then, using Newton's laws of motion, you could calculate the tension on the tether. And that's when everything fell apart. It turns out the stress on the tether would snap steel. Steel, the hardest substance known to science back in the 1800s, would snap if you built such a tether. Well, that's the way it went for 100 years until the creation of nanotechnology. Now we have carbon nanotubes that in principle are strong enough to keep the tether from snapping, meaning that space elevators may actually be possible. However, what's the catch? The catch is that the amount of carbon nanotubes is much larger than that we can produce at the present time. In other words, we can only produce small quantities of pure carbon nanotubes that are stronger than steel, about a centimeter or so. But we need a tether longer than a centimeter. We want a tether that is thousands of miles long into outer space. So it's an engineering problem. It's a technical problem. There's no law of physics preventing us from creating a space elevator. But the technical problems are horrendous. So if somebody in the audience can find a way to create pure carbon nanotubes that are thousands of miles long, you will go down in history as the Thomas Edison of outer space by creating a space elevator. Okay, let's take the next listener phone call.
My name is William. Give me any suggestion about getting a layman's level book about magnetism and electricity. I would be interested in getting a layman's level book of that. Thank you very much.
Well, I've written a bunch of books for laymen, however, not about electricity and magnetism. However, on the Internet, I was searching the Internet the other day, and there really are some good books written for the layman concerning electricity and magnetism. But once you learn about that, and you want to know about gravity, and you want to know about universes, and you want to know about quantum theory, then you may want to get a copy of some of the books that I've written, including Hyperspace, Parallel Worlds, and Beyond Einstein. Okay, let's move right along to the next listener phone call.
Hi, this is Tim. I'm calling from Michigan. My question regarding thermonuclear fusion. There are principally two types of method of thermonuclear fusion that are pursued by humans on Earth, the inertial confinement method and the magnetic torus method. My question is, are there examples of these two types of attempted fusion processes in nature? Thank you.
Well, the answer is yes. Look at the sun. Why does the sun shine? Why do the stars twinkle? Because they are gigantic thermonuclear fusions. Gravity compresses hydrogen gas to the point that the interior reaches tens of millions of degrees. At that point, the hydrogen fuses with other hydrogen, creating helium, releasing excess energy in the form of thermonuclear fusion. And so nature, Mother Nature, uses the nuclear force to light up the heavens. That's what gives us the fuel that lights up the stars. Now, you mentioned two types of fusion on the Earth. One is laser fusion, where I have a pellet of hydrogen-rich material like lithium deuteride, and I shoot it with a bank of laser beams spherically, symmetric, so that the pellet implodes. The surface of the pellet is incinerated and implodes, creating temperatures not seen since the center of the sun, and that's what causes laser fusion to take place. In Livermore National Laboratories, I actually took a film crew from the Discovery Channel, and we actually filmed at the Livermore National Laboratory, where we have such a device. However, it's not commercially available, unfortunately, so we're not going to get usable amounts of commercial energy from that device. The other device is being built in France, southern France, in Cardache, France. That's called the ITER fusion machine. It uses magnetic fusion. It uses magnetism to confine the hot gas, not gravity. Mother Nature uses gravity of stars to compress the gas. In southern France, we use magnetism to compress the gas. However, that doesn't work yet either. So at the present time, we have no thermonuclear device commercially available. But one day, we think fusion power will give us unlimited energy from seawater. Seawater is the source of hydrogen that we will use for our laser fusion stations. But we don't have them yet. Okay, well, unfortunately, that's it for Science Fantastic.
Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And once again, in this hour is your hour. Okay, well, let's move right on to the next listener phone call.
Chad in Lewisburg, West Virginia. My question is, how do you go from matter being non-living to living? Thank you very much.
Well, you ask a question which goes to the heart of the controversy about biology. Several hundred years ago, people believed in something called spontaneous generation, that life could spring from ordinary inanimate matter all by itself. And to prove that, they did an experiment. Take your dinner table and simply leave it out overnight. Well, the next day, sure enough, there are flies, there are maggots, there are all sorts of insects in your food. And so that was, for many centuries, considered to be a proof that spontaneous generation takes place, that life can spontaneously occur from matter. Simply leave your dinner table out overnight. Well, along comes Louis Pasteur and many of the advocates of the germ theory, and they said no. You do not have spontaneous generation of life. Simply take life, for example, your soup that you had tonight, boil it to sterilize it, and put a cover over it. And then the next day, you'll find that the soup is still fresh as ever. And so spontaneous generation of insects take place because insects land on your food and create eggs. Then the next big jump was when we scientists begin to figure out how this process actually takes place. This was done in the 1950s by a graduate student of Nobel laureate Professor Urey. What he did was an experiment that shook the foundations of biology. He simply got a flask of water, put into it some of the elements that we think were present at the beginning of the Earth. He put an atmosphere of ammonia, methane, hydrogen, a real nasty atmosphere, sealed the bottle, and then put a small electric spark. Well, then he walked away. He just walked away from this experiment. A few months later, he came back and he analyzed what was inside the flask, and he found, much to his shock, that he found amino acids. Amino acids are the building blocks of proteins. Proteins are made out of amino acids. And so in other words, he made a paradigm shift. He proved that if you simply get a flask of hydrocarbons, like ammonia, methane, poisonous chemicals, hit it with an electric spark, you get the seeds of life, the precursors of life, amino acids, which are the building blocks of proteins. Since then, we have found amino acids in comets, amino acids in meteorites that have fallen on the planet Earth. And this is now considered to be the best indicator we have of the origin of life. According to this theory, and of course there are variations of this theory, life probably started in the oceans, where there is a liquid called liquid water, which acts as a mixing bowl for DNA and amino acids and proteins. And so you mix all these chemicals together, but you need energy. We think that the original energy of life probably came from maybe volcano vents at the bottom of the ocean. At the bottom of the ocean, we see very hot volcanic vents that release toxic chemicals like methane and ammonia, but also have enough energy to create the first chemicals of life. And so we think that the first amino acids, the first proteins, and the first DNA was created at the bottom of the oceans. But once you have one DNA molecule, it reproduces itself. Then you have two. From two, you have 4, 16, 32, 64, 128, ... And pretty soon, you have chains of DNA giving you the basis of life itself. And then, of course, the DNA had to protect itself, created a cell around it, and that began life. Life that is single-celled, reproducible, starting from nothing. Okay, let's move right along now for the next listener phone call.
Mike from North Dakota. My question is, the Hadron Collider, how will that exactly prove multiple universes? Thank you.
Well, you ask a very interesting question. As I said before, the leading theory that explains the nature of gravity, the nature of subatomic particles, is something called string theory. And you may say to yourself, well, smarty pants, if string theory is the theory of everything, then why don't you guys get the Nobel Prize for string theory? Well, there's a problem. You see, everything has to be verified. You just can't say that, hey, I have the theory of the universe. No. You have to test it in the laboratory. And string theory makes all sorts of crazy predictions. Not only does it predict the subatomic particles that we see today in the laboratory, it predicts whole generations of subatomic particles that we haven't even seen yet. In other words, we can predict what the next batch of subatomic particles are going to be, because these are the predictions of string theory. But unfortunately, the Large Hadron Collider is not powerful enough to test all the indications, the predictions of string theory. Now, the critic of string theory would say, well, the most outrageous prediction of string theory is that our universe is not really three-dimensional at all. Most of us think that the universe is three-dimensional. We have length, width, and height. 3 numbers describes any object in the known universe, but not string theory. String theory predicts that the universe is 10, maybe even 11-dimensional. And that upsets some people, because how do we test this theory? Well, there's several ways of testing it. First of all, with the Large Hadron Collider, we hope to create some of these new subatomic particles, which are vibrations in a higher dimension. These subatomic particles are called dark matter. Dark matter, we think, surrounds the Milky Way galaxy. There's probably dark matter in your living room, but it's very hard to detect. It's invisible. It has gravity, but it's invisible. You can't see it. And so we think that dark matter holds the galaxy together. In fact, I think the Nobel Prize will probably be given to astronomers in the next few years who have been able to map dark matter. But we want to create dark matter in the laboratory. We just don't want to conjecture it to be outside the Milky Way galaxy. No, we want to see it in the laboratory. And that's where the Large Hadron Collider comes in. Another way to test string theory is to put gravity wave detectors in outer space. We have now detected gravity waves on the planet Earth. That made headlines a few years ago when that was first discovered. And, as I mentioned, the Nobel Prize will probably be given to those physicists who detected gravity waves on the planet Earth. But gravity waves were also emitted at the beginning of time, at the instant of the Big Bang. So in other words, we're going to get baby pictures of the infant universe as it was created. And maybe we'll see evidence of an umbilical cord connecting the infant universe to a parent universe, a parallel universe. Of course, we don't have this detector yet, but there are plans to launch something called LISA, Laser Interferometry Space Antenna, into outer space, which would have, we think, the capability of detecting radiation from the instant of creation itself. This is truly amazing. Okay, let's move right on to the next listener phone call.
My name is Dylan. I live in Sandpoint, Idaho. I'm calling about time travel and hoverboards, because I've watched Back to the Future. I want you to discuss that. Bye.
Okay, well, everyone who's ever watched Michael J. Fox whizzing around the past on a hoverboard has wondered about those two things. Are hoverboards possible, and is time travel possible? Well, let's take these one at a time. First of all, hoverboards. Hoverboards do not exist. You can go to any hobby shop and ask for a hoverboard, and you'll simply get snickers from the salesperson. Everybody wants to know, is it possible to have hoverboards? And at the present time, the answer is no. Does that mean they violate the laws of physics? No. One day, we may have something called room temperature superconductors. That is, magnets which are superconducting with no resistance at all. The problem is that you have to cool magnets down to near absolute zero before they become superconducting and become supermagnets. Maybe one of these days, maybe somebody that's listening to my voice right now, maybe somebody that's an amateur wondering about that movie, will create a room temperature supermagnet. If you could do that, not only would you be considered the next Thomas Edison, you would also get the Nobel Prize in Physics to boot. A room temperature superconductor. With that, you could probably create a version of the hoverboard in Back to the Future. But at the present time, nope, we can't do it. Now, time travel is much more difficult. So let's say a few things about time travel. First of all, Einstein said that time is a river which meanders its way across the universe, speeds up and slows down. We measure this all the time with our instruments. Time does speed up and it does slow down. But we want whirlpools in the river of time. We want the river of time to take us backwards in time. Well, if you look at Einstein's equations, you see, yes, there are solutions of Einstein's equations which give you time travel. Whirlpools in the river of time. So what's the catch? There's always a catch someplace, right? The catch is you can also use Einstein's equations to calculate the energy necessary to bend time into a pretzel. And it is fantastic. You're talking about perhaps the energy of a black hole, the energy of an exploding star. So in other words, we are far below the threshold necessary to harness the energy necessary to play with black holes and also play with time machines. So, sorry about that. Now, however, that doesn't mean that perhaps aliens in outer space that are perhaps thousands, millions of years ahead of us, perhaps they've already been able to harness Einstein's theory to create whirlpools in the fabric of space and time. Now, then the question is, if time travel is possible for an advanced civilization, then why don't we see tourists from the future? That's the criticism raised by my colleague, Stephen Hawking, the physicist. He said that, well, if there are time machines, then where are the time travelers from the future? Where are the tourists from the future? Well, my attitude is that we will probably have invisibility long before we have time machines. So maybe they are invisible. Maybe the time travelers are already here, and we're just too stupid to know it.